everyone, I'm Xiao. I'm glad to be here to present our work, JBomAudit, assessing the landscape, compliance, and the security implications of Java SBOMs. So in recent years, the software supply chain attacks has growing so fast. High-profile incident includes like SolarWinds, Log4j, and executils have impacted millions of users and organizations worldwide. So with those attacks increase, it is critical to understand those risks and find a way to mitigate it. One of the biggest concerns in the software supply chain is the lack of transparency. When the developer integrates libraries, they don't always know what is inside. The vulnerabilities may go undetected and leave the software exposed to the software supply chain attacks. This brings us to fundamental questions. How can we enhance the transparency within the software system, and what strategy can effectively detect and prevent software supply chain attacks? To address these issues, government bodies and regulators worldwide, like the US, UK, and Canada, have advocated the adoption of the SBOM solution. This is SBOM is short for Software Bills of Materials. So the SBOM established an inventory list of the software components, and it helps the organizations to have a visibility of what is inside of the software and help them to identify vulnerabilities and mitigate the vulnerabilities. Let's take a close look at what is a SBOM. It is essentially an ingredient list of software components, detailing some information related to the metadata, components, and dependencies. SBOM plays a crucial role for the vulnerability management by providing the visibility into the software. Many vulnerability scanners are built on top of the SBOM by cross-referencing the dependency with the vulnerability database. They can enable quick identification and resolution of the potential issues. To regulate the SBOM and ensure the quality of the SBOM, the national agency NTRA actually established a minimum requirement for SBOM compliance. They require SBOM must provide a comprehensive and correct list for the top layer dependency and their transitive dependency on the second layer. However, our study finds that most SBOM fail to meet those requirements. So let's consider a real-world example. A dependency that actually used in the code but is not disclosed in the SBOM. As shown in the left figure, there is a class file called org JBOS VFS class. It's dynamically loaded and actually used by the code in the VFS utils.class. However, this direct dependency is missing in the SBOM, which means that this SBOM failed to meet the NTIA completeness requirement and making this SBOM non-compliant. If the SBOM has the missing dependency, the vulnerability associated with this missing dependency may go undetected because the vulnerability scanner built on top of SBOM. If this dependency missing, that means that the vulnerability associated with the dependency will also not visible to the vulnerability scanner. So in our study, many focus on the SBOM in the Java domain. This is because the SBOM adoption in other languages are still in the early phase. We are unable to collect a significant number of SBOM for the projects written in C, C++, Python, or other languages. In the Java domain, we are able to collect more than 25,000 SBOM and its corresponding jar files. And in our study, we proposed a formalized consistent model to compare different types of inconsistency between the SBOM and the actual code. We also develop an end-to-end tool to detect those different kind of inconsistency, and we also performed a large-scale measurement study to understand the prevalence of those non-compliance and their root cause and the security implications. In our study, we identified two broad types of dependency issues: missing dependency and incorrect dependency. The missing dependency are the components used in the distributed code, but not listed in the SBOM. It may lead to potential security oversights. For example, if a missing dependency has a vulnerability, it won't be tracked by the vulnerability scanner built on top of the SBOM because this dependency is missing. And the security team may never fix this vulnerability and eventually will leave this software vulnerable to those attacks. And we also categorize the missing dependency into different types, like missing direct dependency, missing transitive dependency, and missing the transitive relationship. And for the incorrect dependency, the definition is that dependency listed in the SBOM, but it is not used in the code. So if you can imagine if the SBOM lists a lot of incorrect dependency, the security team may waste time to investigate and mitigate risks that don't exist. It will distract the security analyzer from the real threats, and also eventually it will delay some fix for more critical vulnerabilities. To detect the different types of inconsistency, we developed an end-to-end detection tool called JBomAudit, and it includes three components: data collection, dependency tree extraction, and the compliance check analysis. For the data collection, we download all the artifacts hosted in the Maven platform, and we use the keyword matching to collect SBOM and its corresponding jar file. And we also, to extract the dependency tree from the jar file, we develop a binary analysis tool called JPKG tags. It essentially will scan the bytecode of the Java class to capture the utilized Java classes from the external classes, method parameters, annotations, and dynamic features. So after we retrieving the utilized Java class, we will recognize the dependency that provided this class and iteratively construct the dependency tree from the jar file. And similarly, we will also parse the SBOM to obtain the dependency tree disclosed in the SBOM. And then we will compare these two trees to identify if there is any inconsistencies. This slide shows the overall result of the non-compliant SBOM detected by the JBomAudit. As we can see, we revealed a significant number of missing dependencies or incorrect dependencies. Especially for the direct dependencies, it is quite concerning because it makes SBOM less reliable, and it also disrupted the tool built on top of SBOM, and it will eventually exaggerate the security risk in the software supply chain. This figure lists the top 15 missing dependency. The top one is a library from Google called Guava. It is the most frequently omitted libraries by the developer. And note that every version of this library released before June 2023 has at least one known vulnerabilities, which means that if this dependency is missing, the vulnerability associated with this dependency will go undetected and will posting the security risk to the software integrator, these libraries. This figure lists the top 15 incorrect dependencies, and those dependencies are commonly associated with a category like the annotation libraries, logging frameworks, or some utilities libraries. We also analyzed the security implications associated with those incorrect or missing dependencies, analyzing their impact on the vulnerability management. And we use a bubble chart to illustrate the distributions of the vulnerability associated with the non-compliant dependency and their impact on SBOM. As you can see, each bubble represent vulnerabilities. And the y-axis represents the severity score of the vulnerability. And the x-axis represents the unique non-compliant dependencies associated with these vulnerabilities. And the size of this bubble represents the non-compliant SBOM affected by those vulnerabilities. From this chart, we can see the majority of the vulnerability actually are rated as a high or critical score, underscoring that the severe security risks associated with those non-compliant SBOMs. You may be wondering why there are so many dependencies are incorrect or missing in the SBOM. So one of the biggest root cause is that most of the SBOM generators are solely related on the metadata, like the POM file, to generate SBOM. They will never actually analyzing the code. However, the metadata maintained by human and they are error prone. So any incomplete or incorrect metadata will lead to missing or incorrect SBOMs. And also those SBOM generators is not sufficient when deal with the more complex Java projects. This is because those SBOM generators solely use the one metadata file to generate SBOM. It will neglect the metadata files like the OSGI bundles or other customized classic file configurations. Beyond of these issues, there are some other root cause like improper usage of SBOM generators or the misunderstanding or interpretations of the SBOM requirements. And you can see the details in our paper. So here is a few takeaways. Our study formalized the SBOM compliance issues, and we developed a tool to detect those issues. We performed a measurement study to understand the issues, and we obtained the artifact evaluation badges. And also, we responsibly reported our findings to the project maintainer, and several open source maintainers have acknowledged our findings, and they have already fixed their SBOM in their latest release. That's all for the talk, and welcome for any questions.
You on this side, whoever you are, gentlemen, go ahead.
Hey, so this is really cool. I'm Aditya from NYU. I had a question. So did you get a chance to talk to the folks who built these SBOM generators to understand why they were looking at what they were looking at to generate these SBOMs? Right? You said that there was a case where these SBOM generators were just looking at just the pom.xml or something like that. So do you have any idea why they made that decision rather than looking at the bytecode, the way you did and so on?
Yeah, I think the current most popular SBOM generators in Java domain is CycloneDex Maven plugin, and they're purely built on the POM file. And actually, we try to communicate with the maintainer of those SBOM generators and to see their feedback about how to improve those ecosystems. But they from the fundamental methodology, they purely rely on the SBOM's POM file. They will not consider analyzing the JAR binary code to generate the SBOM.
I see. So they're just not open to the idea.
Yes.
Okay. Interesting. Okay, cool. Thanks.
Mm-hmm.
Hello. Thank you for the interesting talk. I'm Sujin from KAIST. I have this one question. So you said that a lot of the root causes of having insufficient or incorrect SBOMs is that there are a lot of mistakes, and also these tools are insufficient. But given the security analysis, how you did the security implications analysis, I was wondering if you saw any hints of malicious intents in generating insufficient or incorrect files. If they're only missing one dependency, and then that dependency has a severe vulnerability, would you consider that as a malicious intent, or is that kind of common?
I won't say the providers of the incorrect or missing SBOMs are malicious. I think they just want to using the minimal efforts to generate SBOM and relied on the third-party vendors tool to generate SBOM, and but it is possible that a malicious actor that will hide their kind of malicious libraries and then will propagate to the downstream user integrated these libraries. It is possible, but it's hard to verify, and I think it's possible, and it is also interesting directions to explore.
Thank you.
Great. I also have one question for you. So ground truth is a really difficult thing to get, basically everywhere. So for instance, if I use code obfuscator on Java bytecode, then your ground truth is not going to be very ground true.
Yes.
So
Yes.
can you talk about any other limitations related to how you assess ground truth? What areas should others who are looking at this work think about as places that they could try to look for differences and things like this?
Yeah, I think this is a really good question, because in our project, the most time-consuming part is to construct the ground truth, because we need to evaluate the performance of our study. So to be honest, we collect 30 real-world Java projects, and we have three experts in Java domain. The engineer spend more than 100 hours to manually analyzing the code and to construct the ground truth. And for that case, if the code they're using obfuscation techniques, of course we cannot guarantee what libraries it use. So we will discuss. We will not use this for our ground truth to evaluate our tool's performance.
Well, let's thank all the speakers again.